Okay, now we're going to first sketch a general exponential graph. You can ignore the labelings in green. We'll explain where those labelings came from shortly. But we see that we do an exponential graph. We have equal intervals on the x-axis, and y doubles whenever x changes by that interval. So we can construct our general exponential graph without a label. Again, ignore the green. That's not even supposed to be there at this point. But since that was there when we finished the board, we kept it there. Okay, so we mark a point on the x-axis. We move the doubling distance, and we double the y value. We move the doubling distance again, and we take the y value, and we double it, and we get this y value. We move the doubling distance again, and this y value becomes this y value. We move backwards this way, and this y value becomes half as great. This added to this gives us this. And move that far again to the left, it becomes half as great. This added to this gives us this. That should be a familiar construction to you by now, and that's how we can kind of quickly construct a general exponential graph. Now, that graph can be labeled to fit any exponential function. And I'm telling you that y equals 1,000 times e to the x is an exponential function that represents how much money we have after x years if we start with $1,000 and compound continuously at 100%. Okay? So this is the money. This is the model. For $1,000 at 100% annual interest, compounded continuously. I wrote the word annually, and I don't have room to write compounded continuously, but I'll kind of sneak it in here. Compounded CPD continuously, C-O-N-T. Okay? Okay, that's the function. Now, this graph can be labeled if we find the right numbers to put in the x and the y axes. This graph can be labeled to model this function. Okay. Now, to do this, we first notice that if x equals 0, x is a number of years, x is our 0 year, what's e to the 0 power? Well, you should know that to be consistent with the laws of exponents, we're compelled to set any number to the 0 power equal to 0. Okay? That's a rule that you're told. You weren't told exactly why that rule holds, but the laws of exponents become inconsistent if that's not the case. So any number to the 0 power is 1. Did I say 0? Any number to the 0 power is 1. E to the 0 is 1. And 1 times 1,000 is 1,000. So that when x equals 0, a 1,000 times e to the x has to equal 1,000. So that means that if we want to label this to be the graph of this function, when x equals 0, y has to equal 1,000. Well, here's where x equals 0, so we got to put 1,000 here. We got to put that there, okay? We have no choice if that's going to be our function because e to the 0 is 1. Okay? Now, the question then is, where is x equal to 1? Now, I've put it here, and I've done some, you see some stuff up here, but let's look at the reasoning. 1,000 multiplied by e to the 1 is 1,000 times e. E is about 2.718. We don't need to use any more significant figures than this. We don't even need that many because we can't see a fourth significant figure on this graph. We can't even see a third. Okay, but I put them down there. That's a little too many significant figures to be significant on this graph, but we'll go with it anyway. Okay, so we multiply 1,000 times 2.718, we get 2,718. This says when x equals 0, when x equals 1, y has to equal 2,718 to be consistent with this green function. So we put 2,718 here, and we ask, well, okay, if we go to the graph point where y is 2,718, well, if y is 2,718, x has to be 1. So we come down here to 1, and now we know where 1 is. To the extent that we've been able to draw this graph accurately, to the extent that the graph is constructed accurately. So here's 1. Now, if we want to know what we get when we compound continuously for 2 years, well, we could come out 1 year, 2 years. So here's 2 years. And we could come up to the corresponding graph point, be somewhere around here, and we could extend the y-axis up here, and we could estimate how high this is. Well, from the looks of it, we go this distance, this distance, this distance. It's about 3 times that far. Maybe a little less, maybe a little more. And we could actually figure out what it has to be using laws of exponents and stuff. It's not hard to figure it out. It turns out that it actually should be a little bit less, but it looks like that number is around 8. Okay? So, if the y value is about 8, which is what it looks like for this graph. And to the extent that this is vertical, you know, if I'm a little off of vertical, that could vary considerably because of the steepness of the graph. But if that's correct, then we have an estimate of how much, we have an estimate that allows us to get how much money we have after 2 years. And I said 8. Actually talking about 8,000. And you might observe, well, 8,000 really occurs here, so that's probably closer to 10,000. That's all right. We're just getting a gist of the graph. Okay. So that's how we could relabel the graph to represent the function 1,000 times e to the x. Now, if we want to label the graph just to represent y equals e to the x, what would we do? Well, I'm going to label the y-axis in, what is that, pink? Whatever this color is, it's kind of reddish, kind of pinkish. So I'm going to say that when x equals 0, y equals e to the x is equal to 1, because e to the 0 is 1. So when y equals 0, this function, this red function, would have to have value 1. So I'm going to double label this point here on the y-axis. And I'm going to label it as having value 1. So there we are. And then when x equals 1, y equals e to the x equals e to the 1, which equals e, which is approximately 2.718. So I come up here and I find 2.718. Well, that's going to be the same y value that or the same point on the y-axis where previously I labeled 2,718 for the function 1,000 times e to the x. So my 2.718 for the pinkish red function, y equals e to the x, would occur here. And then where would x equals 1 occur? Well, we take that 2.718, which is here, we project over here and down, and we find that the projection line is identical to the green projection line we used, and our 1 is still here, so 2 is still here. So if 1 is here and 1 is here, this graph represents y equals e to the x.